Hello, my name is Mohammed Ibrahim, and today I'll be presenting my project titled 2D Fluent Flow of NACA Airfoils. This project simulates and compares two different airfoils, the NACA 6409 and the NACA 4418, under cruise conditions similar to those experienced by Boeing aircraft in the air. In this study, I used Anson's Fluent to simulate the performance of the NACA 6409 and the NACA 4418 airfoils. The simulation model's cruise conditions are 250 meters per second of air inlet at 40,000 feet, with a Reynolds number of approximate 1.3 million. I varied the angle of attack from -5 to 20 degrees and focused on measuring lift and drag forces. Through mesh refinement, geometry checks, and solver convergence, I ensured reliable results. Ultimately, the NACA 6409 proved to be more efficient, producing higher lift with lower drag. My motivation for this project came from a long curiosity of how can something as heavy as an airplane stay in the air for a long period of time. To understand that, I study how airfoil shape affects lift and drag. Airfoils are labeled using NACA systems. For example, the NACA 4418 means 4% camber located 40% from the leading edge and 18% thickness. The idea of using airfoils dates back to early aerodynamic pioneers like Cayley, Lithenthal, and the Wright brothers, who laid the groundwork for modern flight we see today. NACA numbers describe the airfoil's geometry, including camber, location of the camber, the thickness. These features determine how the air flows through around the airfoil. Today we simulate airfoils using CFD instead of physical wind tunnels. Airfoil design plays a key role in aircraft, wind turbines, and even Formula One cars. Here we talk about the geometry of the airfoils in detail. The NACA 6409 airfoil has 6% camber and 9% thickness. These two numbers came from the title of the NACA airfoil itself, as the first number of the NACA digits of the four digits represent the camber, and the last number represents the thickness. The NACA 4418 has 4% camber and 18% thickness, as the last two digits define the thickness of the airfoil. Both have a chord length of 0.1 meters. The difference in shape is significant between the two, but however, the NACA 6409 is thinner and has a more curvature, which affects how air flows around it. For my simulation, I used Anson's Fluent for the simulations. The main governing equations are the Reynolds average Navier-Stokes equation, the model turbulent flow, I calculated the Reynolds number using flow velocity and chord length and used standard equations to extract lift and drag coefficients. For my mesh, I created a square domain to ensure the airfoil wouldn't touch the walls when rotated from different angles of attack. As I said earlier, the inlet velocity was set at 250 meters per second. The top and bottom walls were slip walls. The right side was the outlet. The right side of the wall was the outlet, and the left side of the wall was the inlet. I refined the mesh through trial and error until convergence was reached. As you can see from my slides, how drag and lift forces change the mesh refinement. For the NACA 6409, the optimal mesh size was 0.04, and for the NACA 4418, it was 0.02. These values gave stable and consistent results, confirming mesh independence. For my solver convergence, to verify solver convergence, I adjusted geometry length 400 millimeters for the NACA 6409 and 360 millimeters for the NACA 4418. The graphs show convergence values at 80 and 300 respectively, and total the simulation ran up to 14 million iterations for some cases to ensure accuracy. My results. This is a pressure contour of the NACA 4418, you can see that the pressure on the top of the surface is lower than the one from the bottom. This is this difference is what creates lift. As you can see from the darker blue color, that the pressure is much higher on the top instead of the bottom. As for the velocity contour, the air moves faster on top than it does on the bottom, which follows Bernoulli's principle, gives it the redder orange color on the top. The lift and drag versus the angle of attack. When analyzing performance, the NACA 6409 reached its maximum lift at about 15 degrees, while NACA 4418 peaked at 11 degrees. After the peak, both airfoils stall. This is when lift drops off sharply. We can also see that camber increases lift. The higher thickness tends to increase the drag. The NACA 6409 performed better in almost every way. It generated lift even at -5 degrees and had the lowest drag at -3 degrees. The 4418, with its thicker profile, had more drag and needed higher angle of attack to generate a more powerful lift. This confirms that the camber and thickness are critical factors in any airfoil design. To summarize, the NACA 6409 is the better airfoil for this Boeing cruise. Its higher camber and thinner profile help it generate more lift with less drag. The simulation also showed how the leading edge and angle of attack affect velocity and pressure distribution. A future direction could be to test combinations of camber and thickness to see if there's an even more optimized shape to help with velocity, pressure, drag, and lift. These are the references that I use, including the Airfoil 2's database, the AIAA paper by Carmichael, and text by Anderson and Pandit. Thank you.